All right, now that we have set up voltage, current, and resistance, we're going to spend this video talking about Ohm's law, which is essentially a relationship that Ohm discovered doing experiments in the early 1800s as he varied the voltage in a circuit. And so what I have pictured here is essentially what Ohm had set up for his circuit when he was investigating the relationship between essentially the power supply or the voltage difference in the circuit and the resistor that was in the circuit and the current that was flowing in the circuit. So let's just take a moment before we talk about the actual experiment to identify the elements in the circuit. So first you've got the battery. So the battery in a circuit is always going to be represented with these parallel lines where they sort of oscillate or alternate between large and small lines. The resistor here is represented by this little sawtooth line. And then the current flowing in the circuit is just represented here by I and then this arrow. Notice that the positive terminal of the battery is on this side, so that means your current is going to be clockwise through this left circuit. The other two elements that are in this circuit that Ohm was investigating is an ammeter and a voltmeter. And so the ammeter is an instrument that's designed to allow you to measure the current flowing through some point in your circuit. And in this case, our circuit is really simple. Our circuit is one battery hooked up to one resistor. And so what you do is you insert the ammeter in series with those two elements. So in series, that means that the current that's going through the battery has to go through the ammeter before it then goes through the resistor. Right, so that's what we mean by series. Now, in order for the ammeter to not affect the current flowing in the circuit, the ammeter resistance needs to basically be 0. So for an ammeter, R equals 0. Because essentially, when you add that ammeter into the circuit, if there was any resistance, then it would essentially change the amount of current being drawn through the battery. Right? So our ammeters have 0 resistance or negligible resistance. The other element here is a voltmeter, and a voltmeter allows you to measure the difference in voltage between 2 points in your circuit. And so you'll notice that the voltmeter is connected on either side of the resistor. So the voltmeter is going to give a reading not of the voltage value or the potential value, but the difference between these 2 points. And the voltmeter, you'll notice, is not hooked up in series with the circuit. As the current goes around the circuit, when you reach this junction, right, the current can either go out this way or through the resistor. And so the voltmeter is hooked up in parallel. Right? This is sort of the definition of hooking up a circuit element in parallel. And so since this is hooked up in parallel, the current, you can think of the current as having the option of either going through the voltmeter or through the resistor. And the way the current decides, as if it has a choice, the current preferentially divides up and goes down the path of least resistance. And so what that means is that our voltmeter needs to have a very large resistance. So I'm writing R equals infinity. So the resistance in your voltmeter needs to be very, very high. So the instruments that we have in our lab, the resistance in the voltmeter is very high. So when you hook it up in this way, it doesn't draw any of the current through the voltmeter. Essentially, all of the current that's flowing through this portion of the circuit makes it through the resistor, right? So both of these cases, the ammeter and the voltmeter, the instruments are designed so that you can measure what's going on in the circuit without actually affecting the measurement that you're trying to make. So all of that to say that Ohm set up this experiment where he had a battery hooked up to a resistor, and he did this twice. He had the battery hooked up so that current would flow clockwise, and then he switched the direction so that current would flow counterclockwise. And what he did was he just essentially his power supply, he was able to vary the voltage difference across the terminals of the battery, and he just measured the current that was flowing in the circuit using the ammeter reading, and he measured the voltage difference across the resistor as he was varying the battery, the power supply. And so when he did that, he got essentially this data here. And so you can see that on the horizontal axis, in this case, on the horizontal axis, we have it looks like the voltage, and on the vertical axis we have the voltage, and on the horizontal axis we have the current. I think in his actual experiment he might have plotted these the other way around because he was varying the voltage. But either way, when you plot out the data, you end up getting this very nice linear relationship between the current that's flowing in the circuit and the voltage difference across the resistor or across the power supply. And so this behavior where the current is directly proportional to the voltage difference across the resistor, this is known as Ohm's law, right? And so from the slope, you can immediately determine what the resistance value is of that element in the circuit, which in this case you end up getting, if you actually determine the slope here of this line, a resistance of about 3.8 ohms. And so this is Ohm's law, that the current through a circuit element is proportional to the difference in voltage across the element. And I keep saying element because we're going to have resistors, we're going to have light bulbs, which are essentially resistors, we're going to have capacitors, we're going to have a variety of different circuit elements, right? And so that's what I mean when I say an element, is that it's sort of a placeholder for anything that might show up in our circuit. And so most of the things that end up in our circuits are what we call ohmic, and that means that they obey this empirical, experimentally verified relationship that when you increase the voltage difference across a resistor or across a circuit element, the current increases in a proportional manner. And then non-ohmic devices would be ones where when you increase or decrease the voltage difference across the element, the current does not increase or decrease in a proportional manner. Right? Those would be non-ohmic devices. So we have sort of defined what we mean by a circuit. We've talked about the difference in voltage across circuit elements. We've talked about current, resistance, talked about Ohm's law. And so now is the appropriate time to start talking about the electrical potential energy that is associated with circuits and the power that gets generated and dissipated by circuit elements. So I've got a simple circuit drawn here, just a battery hooked up to a resistor, right? And I've got the current drawn with the red arrow. So I've got a current counterclockwise clockwise in this circuit. And I just want to take us back to the definition of power, right? That's the change in energy over the change in time, or it's the rate of energy production. So in a battery, the power, right, this definition, we can think of the energy, right, that is that's associated with our charges moving through the circuit. That energy is essentially potential energy. The point of the battery in this circuit is the battery essentially does work and takes our charges from low potential energy to high potential energy. And then as the charges make their way through the circuit, as the charges move through circuit elements like the resistor, that potential energy is decreased. And where does that potential energy go? Well, the charges don't speed up, rather thermal energy is generated, or light energy is generated if it's a light bulb, right? Some combination of light and heat. So the change in energy is really related to our charges that are moving through the circuit and the moving through a potential difference, right? So that's where the delta Q, delta V comes from. Now, I'm using delta Q here because we're talking about all of the charges that move past a certain point, right? Move across a certain voltage difference in a certain amount of time. So we don't care about just one charge, we care about all of the charges that happen to be going through that potential difference in that time delta T. And so delta Q over delta T is just the definition of average current. And so the power generated by a battery is just this expression right here. So the power generated by a battery is the current moving through the battery multiplied by essentially the voltage across the battery. Now, in the next chapter, we're going to talk about something called the EMF, which is essentially, for an ideal battery, is the same thing as the voltage measured across the battery. But until we get to talking about the EMF, this will sort of serve as our idea for the power generated by a battery. I times the voltage rating of the battery, if you will. Now, for a resistor, so the battery is generating power. Well, the resistors, or the elements in the circuit, all of those elements will be dissipating power. And it turns out that all of the power that's generated by the battery gets dissipated by the circuit elements. So that if you were to make one trip around your circuit, the total change in energy is zero. All of the energy increases were essentially canceled out by energy decreases as the charges move through the circuit. So what that means is that for our resistors, where we have Ohm's law, we can just plug directly into this power expression. So the power dissipated by a resistor will be the current flowing through the resistor multiplied by the voltage difference across the resistor. Or we can sub in Ohm's law and get that the power is I squared R. Or substitute in differently and get delta V squared over R. Each of these three expressions is equivalent. It's the power dissipated by the resistor or the circuit element in your that you're analyzing for. So again, I is the current through the resistor. Delta V is the difference in voltage across the resistor, and obviously R is the resistor value. And then the last thing for this video is that the book has this clever little graphic that you can refer to remind yourself of the relationships between these four quantities: the power, the current, the resistance, and the potential or the voltage. And so I would put this in your notes or refer back to this as we begin working through circuits. Eventually you'll get to the point where you don't need to refer to this, but for these initial stages, that's something that you probably want to keep handy. The other thing I'll point out is that I'm using delta V in my expressions, like right here, rather than just V. So the book kind of interchangeably uses V for the potential value and then also V for the difference in the potential. And I'm trying to remember to always use the delta V whenever I'm referring to the difference in voltage at 2 points rather than using the V notation that the book uses. So when you're comparing what I'm writing here to what you see in the book, that'll be one difference, and that's one of the reasons why I'm doing it, is because we're really talking about the voltage across something. We're not talking about the potential at a given location.